So the recording has begun, and we are going to formally begin our lecture on today. It's about concavity and graph scratching. Yesterday we was talking about similar thing. Yesterday we have displayed how you could actually sketch a graph given that you know the sign of dy dx. Right? So that was what happened yesterday. So basically, let me see if I can draw on this. Just a quick recap of what we have done yesterday. So if you have a graph of functions like this, and you given a function fx, then what you do is you calculate the critical point, then you mark the critical point on the graph at say x1, x2. If, for example, there are two critical points, first it at CP1, which is this one, and there's this one. Then you separate the functions into regions that are separated by the critical points. Then what you do is you work out the sign of the functions in the three regions. Say this is region number 1, region 2, and region 3. Then by checking the sign of the derivative at the 3 point, then you'll be able to know whether the function is going up or going down in these three regions. Right? So for example, if f prime is positive in region 3, then you know the function must be going up when x moves to the right. So by doing these sort of things, then you can join up the graph and provide a sketch to the shape of the functions in these three regions. Then the function, if it's continuous, then it has to go through the critical point. So you join up the graph. So this is one of the example of graph sketching. But as I mentioned yesterday, if you have a graph, there are two ways how the graph can be sort of like changes, right? So if you know the graph is increasing in a region, it may not be enough for you to sketch the graph correctly, because your graph could be going up, right? But going up itself is not enough, because say you have a graph that say that could be going up in this manner. It could also have a graph that is going up in this manner, right? You can also have a graph that is going down in this manner, and you can also have a graph that's going down in this manner, right? So you have to make a distinctions between the trend of how the graph is increasing, right? So not only the graph is increasing, but the trend, right? Not to say the trend, the concavity. That is what I want to say. Okay, so yesterday we mentioned about the concavity. For example, you look at this graph, right? So see if I can use a pen to denote it. Not this one. Okay, so you look at this graph. Let's see if I can show a screen. Yeah, I think I have this marker here. This one? No. This one. Okay, I think I lost control over the my screen for a moment. Sorry about that. Okay. Okay, so let us look at this graph. So I'm moving my mouse to show the portion where I want you to look at. So if you look at this part of the graph, it is going up, but it has a trend that is concave down. If you look at the graph that is on the right-hand side of the x-axis, the graph is going up, but it is going up in a concave up manner. So you have to make a distinction between two types of concavity. That is, whether a graph is having a positive concavity or a negative concavity. So the concavity has nothing to do with the trend, whether a function is going up or going down. Like for example, here you have a function that is increasing. This is also a function that is increasing, right? So this is a function that is increasing. This is also increasing, but this is increasing with a down concavity, and this is increasing with a up concavity. Now this is a graph that is going down. This is also a graph that is going down, but this graph is going down with a negative concavity, or we say concave down. So concave down and negative concavity is referring to the same thing. It's just a different way how you specify it, how you say it. This is a graph which has a positive concavity or concave up. This is a graph that is also concave up, or it has a positive concavity, right? So if you look at these sort of things, then you should be able to tell whether a graph is having a positive or negative concavity. So look at this one. This has a negative concavity, it's concave down, and this is concave up. So if I ask you, say for example, if I draw a graph for you and see if you can tell whether it's concave up or it is not. Okay, it should be quite simple. Say you have a function that is like this. Okay, so is this functions concave up or concave down? So the answer is it's concave up. Right? It is like a bowl. A shape of a bowl that is like this is a bowl that is facing up. Therefore, we said this kind of function is concave up. So be reminded that the concavity of the function has nothing to do with whether the function is decreasing or increasing. It has nothing to do. So graph could be increasing, it could be decreasing. Both could still have a positive concavity or the otherwise. And you could have another function that could be like this, right? So this is a function that has a concavity up or concavity down. So this is a function that has a down concavity, right? Because it is like a bowl that is like having the face facing downwards. So this is a graph which has a negative concavity or which is concave downwards. So I would like to remind you that the concavity has nothing to do with the trend of going up or going down. So this is very similar to a situations of your velocity and acceleration. Right? So you remember in your ZCA 101, you could have a graph, a object which is moving with some non-zero velocity, with a positive velocity, but its acceleration could be negative, could be positive, right? So if its acceleration is positive, velocity is positive, it means it's moving faster and faster. You could have a situation where velocity is moving positive, but the acceleration is negative, right? So it is moving in the same direction, but it's getting slower and slower. So don't mix up concavity and whether a function is increasing or decreasing. So these are the two things that I would like to remind you. So this is what I was saying. So a functions could have a trend. When I say trend, I mean the function is either going up or going down. So the trend of a function, whether it's going up or going down, is described by the sign of the derivative. So a functions, let me see if I can draw it here. When you look at the functions, you should understand that the functions has could be a function that is going up or it is going down, right? So this is what I call a trend. So a function has a trend, and whether the trend is a function that is going up or going down, whether it's increasing or decreasing, depend on the sign of the derivative of the function. So this is the first thing about the graph. It is like you have an object that is moving, so it has a velocity, right? So the velocity is just a velocity. Then at the same time, a function could also have what we call a concavity. The concavity of a graph would be like concave. This is concave downwards or concave upwards. And whether a function's concavity is positive or negative, it depends not on the sign, but it depends actually on the sign of f prime prime. Okay, so remember this. You monitor the sign of f prime to determine a function is either going up or going down, but it means it's increasing or decreasing. You monitor the sign of f prime prime in order to determine whether the function is concave up or concave down. So every functions have a f prime and f prime prime, right? So by looking at the function's sign for f prime, you will be able to tell whether the function is increasing or decreasing. By monitoring the sign of f prime prime, that is the second derivative of the function, then you would know whether the function has a positive or negative concavity. Now, this is very similar to the case of velocity and acceleration. If you look at the sign of our velocity, then if it's positive, it means it's moving to the right-hand side. If it's negative, it means it's moving to the opposite side. And if you look at the sign of the acceleration basically is just a second derivative of the position, right? So if you monitor the sign of the acceleration, if the sign of the acceleration is positive, it means it's moving faster and faster. If the sign of acceleration is negative, it means its velocity is getting more and more negative. So these are the sort of like analogy, right? The f prime is like the velocity, f prime prime is like the acceleration. So the sign of f prime and the sign of f prime prime, they represent two aspects of the functions. Like one, f prime refers to the trend, f prime prime refers to the concavity. Okay, so take note of that because people tend to confuse between the trend of the function and the concavity. So you should not get confused. Okay. Okay, so that is what I want to tell you. I have defined what is concavity and what is a concave up and concave down. So if you look at a function that is having a up concavity, okay, so a function that is having an up concavity would be looking at like this. So the function that is having an up concavity is like this. So what you do is you look at this concavity. I will write it concavity up, right, or concavity positive. So if you monitor the slope of the concavity at different locations, so this is the concavity, the slope on the graph that has a positive concavity. So at this is at x1, this is at x2, and this is at x3, right? So you could monitor the slope of the tangent line for a graph that has positive concavity. And what you find is that you find that f prime, which is the slope of the function, when you move from the left to the right, it is actually become more and more positive. So it means this one is increasing. That is, for a graph that has a positive concavity, the sign of the derivative is increasing. So this is actually what this graph, this slides try to tell you. If you look at the derivative of a graph, if the graph derivative is increasing on an interval, then necessarily it would mean functions that has a up concavity. So similarly, if you look at the functions, you monitor the functions that has a downwards concavity, is like this, for example, right? So then you monitor the slope. Say I draw another cut with another color. So you start off with a point which is okay. Let me try it here. Let me drop off this one. Okay, so a graph, you monitor the slope at a point here, x1, then you monitor the slope at another point, then you monitor the slope at another point. So you find that the values of the slope on the left, which you say x1, this is a point x2, and this is a point of x3. Right? So you look at the slope at x1, x2, x3, then you will find that the values of the slope at x1 is like it is a value which is positive, then it would decrease to become less positive and towards 0. When you go to the right hand side, you move x to the right hand side, the slopes become negative, right? So this is a slope that is negative. This is a slope which is positive. And when you move to the right, the slope will become from more and more positive towards 0 and towards negative. So this is a situation where the slope of a graph that is decreasing. So for this kind of situation where the derivative of the function is decreasing, it represents a graph which has a negative concavity. Okay, so negative concavity is necessarily associated with a graph where the derivative is decreasing, right? So in sometimes I get confused and could get forgotten whether what the concavity up means and what the concavity negative means. So concavity up means a function that has a derivative which is increasing. So based on these definitions of increasing derivative, you can actually work out the shape of a function which has a concavity up and vice versa. Okay, so so now we have already declared, explained quite thoroughly what you mean by the concavity of a function. So now we look at the derivative test, the second derivative test, which I mentioned a little bit just now. That is, if you check the derivative, second order derivative of a function, and if you find that the derivative, the second order derivative is positive, that means the graph is having a concavity up. If the derivative of the function is negative, if the second order derivative is negative, then the function is concave down. So you have actually two ways of determining whether a function has concavity up or down. First is by monitoring whether the derivative of a function is increasing or decreasing. From there, you'll be able to tell whether the graph is concave up or concave down. Right? For example, if f prime is increasing, then it represents a graph that is concave up. If the derivative is decreasing, then the graph is concave down. And so to work out whether a graph has a positive or negative concavity by monitoring whether f prime is increasing or decreasing is slightly more troublesome, right? So you have to look at the trend. You have to imagine whether the trend of f prime is increasing or decreasing when you move to the right. So using these definitions to work out whether a graph has positive or negative concavity involving monitoring the trend of f prime could sometimes be more troublesome, but there is a better way to tell whether a graph is it has positive or negative concavity simply by just monitoring the sign of f prime prime. So if you look at the sign of f prime prime within some interval, and if the sign of the functions within some interval which is positive, it means it has a positive concavity. So let me see if I can draw what I meant by that. Okay, so this is like you have a functions within some intervals of I, and what you do is you monitor the f prime prime. And if you find that f prime prime is positive for x within the intervals of I, then you would be sure that within this interval, the concavity of the functions is positive. Right? It should be a graph that is having a positive concavity that have the shape that looks like this. Well, it doesn't really mean its shape it looks like this, but it must have a concavity which is up. Right? So if you have a situation where the f prime prime is negative within this one, then so just like for example, if f prime prime is negative, then the shape of the graph, the concavity of the graph would be like a negative one, where it must have these kind of situations. Right? So these are a very easy way, a relatively easy way to determine the concavity of an function. Okay, so that is the slide that mentions to you how you check the concavity of a function. So again, the concavity of a function has to be defined over an interval. So at different intervals, you could have different concavity, just like these functions, right? So within the interval from -infinity to 0, the graph of x cubed has an downwards concavity. and then on the right hand side of x, the function has a positive concavity. So when you specify the concavity, you have to specify over which intervals the graph has that concavity. This is very similar, exactly the same as a case where you want to say a function is increasing or decreasing. You have to specify within which interval. So in general, you could divide the functions into a few regions depend on its concavity. For example, you could break up the graph according to the critical point 1 and 2. Then the critical point will sort of like split the functions into a few regions, where different regions has different sign for f prime, and this different sign of f prime at different regions will mark whether the function is increasing or decreasing. Now, apart from that, you can also have a situations where you have to separate the graph into a few regions, right? So these few regions will have to be separated not by the critical point, but by a point where the f prime prime is set to be 0. So you call this point where the f prime prime equals to 0 as what we call an inflection point, if I'm not mistaken. So in that case, you have to separate the graph into the inflections point. Then you have to check the sign of f prime prime in each region to determine the concavity of the graph in these 3 regions. So the idea is very similar, okay? So in order to plot a graph for a functions, you have to know the region where the graph is increasing or decreasing based on the sign of f prime. At the same time, also, you have to take care of the concavity of a graph within that interval. So you have to again find out the boundary at which the concavity change sign, and then on the left-hand side or right-hand side of some regions, then you have to sketch the graph with the correct concavity. So this will be illustrated in the next few slides. In particular, we are going to look at, let's see if we look at this example. We are going to learn how to sketch the concavity of a graph based on the definitions of the second derivative test for concavity. After that, we are going to then try to learn up how to sketch the graph based on their concavity. So this would be quite a complicated situations. So be prepared for that lah. So we are going to do this graph sketching step by step. So until this stage we have learned how to sketch a graph based on their trend, that is whether it has a positive or negative trend and the critical point, and then we also learn how to mark the local maximum and local minimum. Then we learn up also now at this stage how to determine the concavity of a functions. Then we are going to see in the next few slides how to sketch the graph with certain concavity. Then we are going to do what we're going to do next is to learn new theorems of how to determine the local maximums. Then at the end of the day, we're going to put everything together, right? So you know how to graph their functions based on their critical point and whether they are increasing or decreasing. Then you also know how to graph the functions based on their concavity. Then you have to combine both aspects, then plot the graph, and then sketch out the graph manually using the technique that we have learned. Okay, so this would be the aim of today's lecture. Okay, so now at this stage we have learned up how to do the how to decide the concavity. Then let's look at a very simple example. You have a function y equals to x cubed, and then you're asked to find the concavity. So basically, this question asks you, I give you a functions. Tell me what is the intervals of the function where the function has a positive concavity, and within what interval the function has a negative concavity. So to answer these questions, you have to know what it means by concavity, and you have to know how to check the concavity of a functions. So to do that, it would be best to check the concavity by using the second derivative test instead of using the definitions of concavity up or concavity down. So we are going to learn up how to do this by looking at sign of the second order derivative in order to help us to determine the concavity. So you have x cubed functions, so it could be quite easy. Let's just see how we do that. Let me transfer it and then write it on my iPad. So I have a situations where the function is x squared, y cubed. Okay, wait a moment. Okay, it should be like this. So my function is y cubed. So in order to determine the concavity of a functions y cubed, then what you do is you take the first derivative. The first derivative is x 3x squared. Then the second derivative is y prime prime is 6x, right? So what we want is to check the sign of y prime prime. So it's obvious that the sign of y prime prime is separated by two regions. That is, y prime prime will become negative if x is negative, and y prime prime is positive when x is positive. You agree with me? Right, so that is very easily. So you look at the expression for the function y prime prime, then you determine by yourself what is the regions or intervals of x where the sign of y prime prime is positive, and in which regions of the x the y prime prime is negative. So it is quite easily be understood to be like this. Then you said, okay, then it is very easy to have the answer. That is when the function is, let me see here, when the functions here, okay, so when the functions is in the region where x is negative, then y prime prime is negative. When x is positive, then y prime prime is positive. So then the answer to this question is very easy. You would then say that for the functions, let me check. I want to write on my iPad. Okay. So based on the very simple calculation I was just shown, for the functions of y equals to x cubed, then you said that y has positive concavity for x which is larger than 0, and y has negative concavity for x which is negative, right? So that is the answer. So the graph is only separated into two regions, the regions on the left of x and the region on x equals to 0, and the right region where x equals to 0. So here you see it has a concavity up, right? It's like a bowl that is going up. Sorry, not this one, sorry. This is not the graph that I'm showing. This is y cube. So y cube has a shape that looks like this. Y cube has a graph that looks like this. I think it's like this, right? So on the left hand side, y prime prime is negative. Therefore, on this region, it has concavity up. Sorry, concavity down, not concavity up, because the negative concavity down because y prime prime is negative. So a graph that is having y prime prime negative, the shape would be a concavity down. The concavity down graph would be like this. But this part of the graph is only not having a downward trend, but an upward trend. But it's upward trend, but it has a concavity up. Right. So let me try to demonstrate to you what you mean by that. A concavity up. Now you see, if you know for sure that the function is increasing on the left hand side of y. So and it has to have a concavity up. So when you sketch a graph, you don't sketch it like this. Like you don't sketch it like this, because this kind of sketch represents type of a graph where it has a positive concavity. So this is not the correct trend for this. It has to be a negative trend. It has to have a negative concavity. So a negative concavity should be a trend that is like this. It is going up, but its graph is like this. Okay, it should be like this. Right. The wrong way, as I said, is to draw a graph which is like this. So this is a graph which is a concavity that is positive. So you should not do that. It should be a graph that has a negative concavity. So it looks like this. Okay, so then on the case of x positive, then the y prime prime, as already proven, is positive. Therefore, it has a concavity up. So a graph that has concavity up should be should look something like this. Like the graph should have a positive concavity. So it starts from here, then the graph has this kind of concavity. It goes up like that. Now, if you draw it like this, then this is wrong. Okay, let me draw it with a more clarity. So if you draw it incorrectly, then the graph is like this. So this is a graph that is going up but has a wrong concavity. The green color graph is a graph that has a concavity which is down, right? So graph like this has a negative concavity. But here we know y prime prime is positive. Therefore, this kind of graph is wrong. So you must not draw the green color line, but you should draw this color line like this one, which is a positive concavity. So by looking at the sign of y prime prime, then you should be able to work out the shape of the graph. The shape here means the concavity. So here we only talk about the concavity, but we have not actually taken into account of whether the graph is increasing or decreasing. Later on, when we want to sketch a graph, not only we have to take care of the concavity, but also to take care of the trend of the function, whether it's increasing or decreasing. When you overlap this together, then for those who are not clear in your mind, you may get a little bit confused. But don't get confused at this stage, at least. So at this stage, you sort of like know by monitoring the sign of y prime prime, what shape should the graph looks like. Okay. So this is another example of y prime, y equals x squared. So you're asked to check the concavity of these functions. So the idea is actually quite simple. Let me change a little bit the design. I need a blank color, a blank line. Okay, so this is a graph. Then we want to check the graph of a function, which is like y equals to x squared. Check for the concavity. Right? Again, when you want to check for the concavity, the question is, tell me the regions of x where y has positive concavity and the region where y has a negative concavity. Then specify which region, which concavity. So to do that, again, simply check the second derivative. So the second derivative could be easily checked by just look at the first derivative, which is 2x. After you have calculated the first derivative, calculate the second derivative, which is 2. Right. So this is the second derivative, which we have arrived at for the simple function of y equals x squared. Then you ask yourself, what is the sign of y prime prime? So here it is very understood easily that y prime prime is always positive for all x in the real part. Right? So if you draw a function to represent, if you draw a graph of the x-axis to represent the function of x squared, then you'll be sure that the functions has a concavity which is always positive. And this function goes through a point x0. So it must go through this one, and the function must be having a positive concavity. So the positive concavity graph looks something like this, right? So the graph of y squared is always positive. So the answer to this question is that for the function y equals x squared, it is always concave up for all regions of x. Right? So this is another example. So it has only one type of concavity. There's no part in the graph where it has a different concavity. Right? So if this is different, then this case, it has two parts where on the left-hand side of x equals to 0, the concavity is opposite to the concavity of the graph on the right-hand side. Okay, so that is like this, y equals to x cubed. So it has two different concavity. For x squared, it has only one concavity. Now for this kind of functions, where y equals to 3 plus sine, then you can easily take the derivative of the functions. So derivative of the functions could be easily obtained. Let me try to draw something on this. So the y prime is then equals to cos x. Then y prime prime is just minus sine x. Y prime prime, it's okay, something is, let me draw it again. So y prime prime is then equals to the derivative of cos x, which is just sine x. Okay, so we see that the sine of y prime prime is a function of negative sine x. So you can look at the expressions for y prime prime. So at different regions of x, the sign of it is changing periodically. That is, you divide this region into this part, right? So for x in this part, which is given by, say, x between 0 and pi, the sign of the y prime prime is negative, right? It's negative. Therefore, for x in this region, the concavity is negative, right? So it has a negative concavity. So if you look at these functions, it is a function that has an negative concavity. So sine negative sine y prime prime is negative. So it has a negative concavity. And when x is in this region, the values of y prime prime in this region, which is for x ranging from pi to 2 pi, the sign become positive. Therefore, this graph has an positive concavity, whereas in this region, the concavity of the function y equals to 3 plus sine x is negative. Okay, so look at these functions and try to convince yourself you know what it means by that. Okay, why is that this part of graph is positive concavity and why is negative concavity? So let me say it again in a more transparent manner. So we divide these functions into two separate regions. Within this region, the functions of 3 plus sine x is a negative concavity. And the regions here, the function is a positive concavity. So this is a function that has a positive concavity. This is a function that has a negative concavity. Right? So convince yourself a function that looks like this is a negative concavity. The function that is like this is a function that is positive in its concavity. Okay, so this is another example of recognizing the concavity of the functions. So in the case of a critical point, right? So for example, when we have a critical point, so you could have a functions where the critical point changes sign, right? So in the case of f prime prime equals to 0 or f prime prime not defined, then you have this critical point, right? So these are the critical points where potentially the f prime at three regions next to the critical point could change sign, right? So this is for f prime. So we have a critical point that sort of like separate the region of a function into regions where the sign of f prime could change sign. Now, similarly, if you are looking at the critical point, at the concavity of the functions, so for the concavity of a functions, you could also have a situations where you could divide the regions into separate regions where the sign of f prime prime may change, right? So this is very similar to the case of the critical point. In the critical point, the sign of f prime may change at the critical point. Here, we talk about inflection point. So inflection point is a point where the sign of f prime prime changes. Like this is very similar to the case of critical point where the sign of f prime change. Right. So the case of critical point, it is a sign of f prime that changes across the critical point. For the case of inflection point, it is the sign of f prime prime that is going to change. So here we define what we call an point of inflection or inflection point. Point where the concavity changes, and at the same time, at that point, you have a functions of tangent line defined at that point. Right. So so what you do is you look at the functions, then you take the derivative of the function, and then you find out the point on the function where the sign of f prime prime changes. And at the same time, at that point where the f prime prime changes, you can also define a tangent line to it. Then you call that point an inflection point. So inflection point basically is involve a very simple calculations. Usually it involves a calculation where you have to calculate the second order derivative and then set it to be 0. So this is normally the first step of identifying the point of inflections. Now, after you have found the point of inflection after you have found the values of x where f prime prime is equals to 0, then you have to look at that point and see whether it is possible to define a tangent line to it. Now, if it is possible to define a tangent line at the point there where f prime prime is 0, then you call that an inflection point. Okay, so inflection point is more or less equivalent in a sense to the critical point. Right. So for the critical point, you use it as an indicator to locate the local maximum and locate the point of local minimum as well. For the inflection point, you use it as a point that locate the change of concavity. Right? So usually the point of inflection has to be marked down in the process of curve sketching, where you have to carefully divide the functions concavity based on the locations of the critical point. So on the one side of the critical point and the other side of the critical point, then you know that at that intervals, the sign of f prime prime changes, therefore the concavity also changes. So let me repeat again. One of the applications of inflection point is to let us decide what is the concavity of the functions when you sketch it, right? So the identifications of the location of the inflection point is important in the process of graph sketching. Okay, so this is a very simple situation. You have y prime. I think this is a better explanations and a better example. This is an inflection point, right? So the inflection point y prime prime is happening here because y prime prime is not in existence. No, maybe let me check this example first before we go to the example number 4. So we have a inflection point to be a point where the concavity changes sign. Then you look at these functions. Now this is a function where you don't have an inflection point. Why is that there has no inflection point? Because you look at these functions, y power 4. For y power 4, the function is y power 4. So you look at y prime, you got 4x cubed. Then y prime prime, you have 12x squared. And it is always positive, right? So it is always positive, larger than 0 or equals to 0. So the y prime prime has always been of the same sign, so it will never change sign, right? So it means the functions of x power 4 has no critical, has no inflection point, not critical point. It has no inflection point. IP stands for inflection point. So this is very similar to these situations. So this is a situations of y equals to x squared, where the y prime prime is always positive. Therefore, again, there's no inflection point because it's never changed sign. Y prime prime never change sign. The graph is having only a positive concavity for all values of x. So is the case of y power 4. It has no inflection point. Now, why is that so? In this case, because the y prime prime is always positive. Now, this example try to illustrate a situation to you. You said the inflection point is not a point where the y prime prime is 0. Inflection point, by definitions, is a point where the sign of y prime prime changes. Okay, so if you have a situations like this, where y prime prime is 0, but it doesn't change sign across x equals to 0, then this is not an inflection point. A point where y prime prime is 0 does not necessarily infer the existence of an inflection point. Inflection point must only be defined as exists if there is a change of sign across that inflection point. Okay, so this is just a counterexample to you. You don't simply say y prime is equals to 0. That must be an inflection point. No, it's not always like this. Now, this is a situations. This is a situations which denotes the existence of an inflection point. Even though at this point y prime prime is not defined at the inflection point. So inflection point definition is quite simple. It just say you have a inflection point if you can define a tangent line there, and the sign of the concavity changes. So here we look at these situations. You have y equals to x power 3, 1 over 3. So this is a situations where I'm going to write it down. Y equals to x power 1/3. Then y prime is 1/3, x power minus 2/3. Then y prime prime become what? Well, y prime prime become minus 2 over 9, x power minus what? Minus 5 over 3. Okay, so it is a complicated functions that, let me write it down in this manner. 9 times x to the power of 5 over 3. I think I look at this more easily. So this is a functions where the sign of y prime changes. That is, y prime prime in this case is negative if x is negative, and y prime prime is negative when x is less than 0, and y prime prime become positive when x become positive. So therefore, it is clearly seen that the sign of y prime prime changes sign at x equals to 0. Wait. Okay, so this is a situation where the left-hand side has an up concavity. Here it has a down concavity for the case of y prime prime, right? So this is y prime prime. On the left-hand side, y prime prime is positive. On the right-hand side, y prime prime. So I think just now I wrote it wrongly. I think there's a negative sign here. So I forgot about this negative sign just now. But anyway, you have you can look at the expression for y prime prime quite clearly, that when x is negative, y prime prime is negative. It's not positive, it's negative because of this sign. Then when x is positive, y prime prime is negative. So y prime prime negative means when x is larger than 0, the graph has a negative concavity. So it looks like a bowl. Let me draw it here. It looks like a bowl that is it's like a bowl where the face is facing down. So this is a bowl. Therefore, this is a negative concavity. On the left-hand side, it's a bowl where the face of the bowl that is facing up. That's how I used to remember whether it's concave up or concave down. So here you have a concavity which is up because f prime prime is positive. Here f prime prime is negative. Okay. So obviously there's a change of sign at this point. And at this point, there is a tangent line that is vertical, right? So there's a vertical line, it's a tangent line, even though the tangent line is infinity, but still is a tangent line. So this is an example of an critical point. It fulfills both conditions. It has a tangent line defined there, and the sign changes at x equals to 0. Therefore, x equals to 0 is an inflection point, right? But if you look at the expression for the y prime prime, the y prime prime is actually not defined at x equals to 0. But that does not affect the fact that x equals to 0 is still an inflection point. So the inflection point does not require the values of y prime prime to be defined, right? As long as the sign at that inflection point changes. On the left, it has a sign of y prime prime, which is different than the sign of y prime prime on the other side. That would make the point an inflection point, even though that point, the y prime prime is not defined, right? So this is the use. So this is an example of how to calculate the inflection point. So calculating inflection point is sort of like straightforward to me. It's not actually that something we should. So at this point, I hope that if I give you a functions, it would be quite easy for you to identify an inflection point. It's just like I give you a functions, it should be easy for you to identify the critical point. Right? So identify a critical point is usually found by setting y prime equals to 0. In the process of identifying the critical point, the process usually involves setting y prime prime equals to 0. Okay, but just be careful that y prime prime equals to 0 does not really necessarily mean the point is an inflection point. Right? But for the case of y prime equals to 0, that must necessarily means that point is a critical point. But these are just minor changes in the definitions. Right? Okay, so now we have already understood what it meant by an inflection point. Then we'll proceed to theorem 5, where we're making use of the second derivative test to identify the local extrema. So you have another set of equations of slides which I have to fulfill, but we are running out of time at the moment. So for your information, after we conclude this lecture, I'm going to continue to record the discussions on this chapter so that I can finish the rest of the slides in the flipped classroom. So hopefully after today, after these sessions, you will click into the recorded lectures for the rest of these slides. So we stop here for a moment. Then I'll continue, and hopefully that you would continue to read and watch the flip class. Okay, so I have already resumed the recording for to continue with our lectures on topic 4.4. So we now arrived at theorem number 5. Theorem 5 is using the second derivative test to locate an local extrema. Before this, we have already defined the f prime prime. I think just now what we have done is that we have wait. Okay. So a minute ago we have just something is not right about this. Sorry about that. Okay. So before that, we have just learned that we can monitor the sign of f prime prime. So the sign of f prime prime, it is positive, then it means it is an upwards concavity. And if f prime prime is negative, then it means it's a downwards concavity. Okay. Um, so this idea of checking the sign of f prime prime could be used to identify the local extremum. So this is the idea of theorem 5. It says you look at a functions, then you look at the function and try to see if the f prime at c if it's 0, and see whether f prime prime is also no. So you check the f prime for functions and see whether it is 0 or not. Then you check the sign of f prime prime at c. Then you'll be able to tell whether it's a local maximum or local minimum. So this is a very simple tricks that I learned when I was in Form 5. So I'm doing it again. So I don't mind repeating it here. It should be just a simple exercise. It's a method for you to locate the local extremum. So what you do is you have a functions fx. Then what you do is you check the point where f prime is 0. So basically you look for the point where the fx is set to 0. Okay, so you look at this point, then you also check the sign. You don't really need to know the values of x where so you don't really need to know the expressions of f prime, but you only need to know the sign of f prime prime. So you look at the values of x where f prime is 0. After that, then you check the sign of f prime prime at c, where c is a point where fx prime is 0. So by doing this, you'll be able to tell whether the point x equals to c is a local maximum or local minimum. So that is for a point where f prime is 0 and the sign of f prime is positive, then it will mean that c is an local minimum. Okay, it's a local minimum. On the other hand, if you have a situations where if you have a situations where the sign of the function f prime prime is negative instead of positive, then that would correspond to an local maximum. Okay, it should correspond to a local maximum. Local maximum. Okay, so this is a case. This is a very simple calculation that allows us to check whether a sign is a local maximum or local minimum. Okay, then the next thing you want to ask is that how come by checking the sign of f prime prime will tells you it is a local maximum or not? Now, first of all, if you have a function where the f prime is 0, it must means the slope there is 0, right? So you have a situation where the graph it has a slope which is horizontal, and then if f prime at that point is negative, it means it's a negative concavity. So that could allows you then to decide that point is maximum or minimum. Now let me look at number one. Let me just I'm just trying to explain to you what the rationale behind the theorem 5. So that theorem needs you to know what is the point where f prime is 0. Now, if f prime is 0, then for sure it has a slope which is horizontal, right? Then furthermore, if you know f prime prime is at the point C is say negative, It means that at this point, the function must be a function which has a negative concavity, right? A function that has a negative concavity must be something like that, right? So you add up these two together. The point here at C, the slope is flat. At the same point, at the same time, the concavity at this point C, it has a negative concavity. It has a negative concavity. Negative concavity is a graph that looks like this. So you combine these two, then you will automatically arrive at a situation where you have a situations where it is C is an local maximum. Now you can do the same thing to the other possibility, that is you have a situation where f prime is 0 and f prime is positive, right? So you combine these two facts into a single picture. So okay, it says you have a graph at the point x equals to c, and that point the function has a slope which is horizontal. So that is translated into this statement. F prime equals 0 translate into the statements where the slope of the function is flat. And these segments is translated into the mathematical fact that the concavity is positive. A concavity that is positive is like this, right? So the graph must go through the critical point here, and it must has an upwards concavity. Sorry, not like this. The upward concavity is not like this. Upward concavity is concavity like the bowl that is facing up, right? So this is a bowl that faces up. So the graph must then be something like this, right? So that indicates the existence of what? This is a local minimum, right? It's a local minimum. So that is how you understand the theorem number 5. Now you could also have a third situation where f prime is 0, but f prime is 0 as well. So in that situation, you cannot say for sure whether that point is a local maximum or local minimum. It could be, it could not be. It is possible you have f prime c equals to 0, but yet it is not a local extremum. It is also possible that point be a local maximum as well. It is still possible. F prime equals to 0, you could still have a local maximum or local minimum, but you cannot be for sure. You cannot be sure. In that case, where f prime is 0, f prime is 0, then to determine whether it is a local maximum or local minimum, then you have to revert to the first derivative test. So usually what we do is you use this theorem 5, the second derivative test, to check whether a point is a local maximum or local minimum. In a case where it fails, such that the f prime at c is 0, then you cannot say whether it's local maximum or minimum. So what you have to do is that you just cannot say, I don't know. You have to revert to the first derivative test. First derivative test is more stronger in this sense. It could allow you to identify a local maximum or local minimum without referring to the sign of f prime, right? So if you failed to identify the local maximum using theorem 5, you may have to refer to the first derivative test. I think last time in the exam we have questions like this. You have f prime equals to 0, but yet it is a local maximum. So in order to determine that it's local maximum or local minimum, you can use the first derivative test. The first derivative test only check on the sign of the f prime on the left and the right, right? So from the sign, whether it's positive, negative, positive, then you can decide whether that point is a local maximum or minimum. So in that sense, as I said just now, local first derivative test can sometimes be more useful than the second derivative test. But second derivative is always the preferred choice because it's much easier to implement. You don't need to compare the sign on the left and the right of the critical point. And then sometimes you get confused when you change from negative to positive or from positive to negative. Then sometimes I got confused as well. Is it a maximum or is it a minimum when the sign changes?